Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, can everybody hear me first? Yeah, okay. So yes, my name is Sophie, and as Andrew already introduced me, a couple of months ago, I have successfully defended my PhD thesis at the Interactive Media Lab in Dresden. And today I will talk about a bit of my work that I have done during my PhD about multimodal gaze-supported interaction. And I want to start with some motivation, kind of driving motivations behind this work. So one was, how can we interact conveniently with large information spaces, such as geographic information spaces, but it can be kind of also, in general, zoomable information spaces, stack of pictures, or more extensive information spaces. And another driving motivation was, how can we interact seamlessly with large and multiple distant displays? So there is an increasing diversity of displays that are surrounding us, and how can we seamlessly interact with them? And one modality that hasn't been kind of investigated much so far is to use our eye gaze to support interaction with such environments. And there are several benefits, or kind of potential benefits, to use eye gaze for interaction. So a couple of very, or rather obvious advantages are that our eye gaze is very fast. It doesn't really require a lot of effort to look at something that interests us, and it is also pretty implicit. On the other hand, it also provides the potential for very seamless interaction with diverse display setups, and it's also a very interesting alternative input channel that can add to traditional ones, for example, using mouse and keyboard and adding gaze input to that. Not so much trying to substitute mouse input, which has been tried a lot of times in other research works, but rather to really think about how can eye gaze support other interaction modalities. And also another potential benefit are attentive systems, so that actually digital systems or computer systems that are surrounding you are more aware of what you're looking at, what you're attending to. On the other hand, there are a lot of challenges actually that make the design of gaze-based interaction pretty delicate. On the one hand, we have the Midas touch problem, which has been coined by Robert Jacob in the early 90s, which simply describes the involuntarily issuing a command via eye gaze. So you're looking at something and immediately something is happening. So this is very overwhelming, of course, for the user. And this is also closely related to the double role of our eye gaze if we want to use it as an input modality, because we use our gaze constantly to observe our environment and also want to use it as a control input. So we have to be aware of that for designing gaze-based interaction. Then another challenge, or at least an aspect you have to be aware of, is that our eye gaze is not a very precise pointing modality. So this is due, on the one hand, to tracking errors, but also it is simply due to the physiological nature of our human vision. So we do not have laser precise vision, so that's why it is pretty difficult to assign one pixel that represents our eye gaze. And these imprecisions can usually be kind of categorized into jittery gaze movements or representations of the eye gaze, and offsets, so that the cursor would be displayed at a point but you're actually looking further to the left or right. Another thing is that a lot of eye tracking systems are visual tracking systems, so they are reliable or susceptible to changing light conditions. So it is pretty difficult to use eye tracking in the wild with changing light conditions, especially direct sunlight is more or less a no-go currently. But there are other eye tracking systems that use other mechanisms for that. And also for the design of gaze-based interaction, one challenge is prejudice. So a lot of participants that I've worked with, they were kind of coming to our studies and kind of already thinking, this is unnatural, I don't want to actually really use it, but they were often surprised actually how good it worked. So talking about the technical challenge, so the eye tracking systems have very improved over the last years, but it is sometimes still common that you have to stabilize the head to acquire high accuracy in the gathered gaze data. However, there are continuous developments, so here are just two examples of a wide range of different eye tracking systems. One is a table-mounted eye tracker from Tobii, which is kind of distant from you, so you're not, it is very inobtrusive because you don't have to wear additional equipment, whereas the head-mounted eye tracker on the right here, you have to wear, of course, and it maybe occludes some of your what you're looking at, your visual field. Although it kind of looks here very obtrusive, usually users really quickly adapt to that and just look beyond the camera in front of their eyes. So these were kind of the basics. So my research has focused on how can we now use gaze as a supporting input modality for distant interaction. And since there hasn't been too much research in this area so far, we have focused on supporting quite basic interaction tasks, such as navigating through virtual information spaces, for example, steering in a virtual 3D scene, and also selecting, positioning, and manipulating distant graphical objects. For this, we have investigated different multimodal combinations of gaze input with other modalities, input modalities. As you can see here, a few examples using mouse, also kind of a way to confirm my action, also touch input from ubiquitous smartphones, or tilting your handheld, your smartphone. And we also considered foot input. And with these multimodal gaze-supported combinations, we can address several challenges that I've mentioned to overcome or to counteract, for example, the Midas touch problem or inaccurate gaze data. And also, in contrast to a lot of studies that use only gaze input to also confirm selection, so you would have to stare, for example, at a graphical button to then confirm it, we can counteract or overcome this time-consuming trailing using such multimodal combinations. Also, there are, of course, different ways to use gaze for applications, eye tracking applications. So here this is a very broad overview. So in general, you can distinguish diagnostic studies and interactive. So our focus was, of course, on the interactive part. Diagnostic would be that you just observe or want to investigate how people look at a website, for example, or how people observe their everyday environment. For the interactive part, we can roughly distinguish three main areas where eye tracking or eye data has been used for interaction so far. A very prominent one is gaze-directed pointing, of course, which we also have focused on, and where you can distinguish different levels of precision. For example, do I really need pixel-precise gaze pointing, or is it enough that I know the rough area of interest? And also different levels of abstraction. For example, am I only interested in a certain target versus a certain point? Eye-based clicking describes that you have to find a way to confirm an action. That is what I've mentioned earlier with the trailing, but there have also been works that try out different blinking behaviors, how you blink with your eyes to confirm an action, which of course was assessed as pretty unnatural. And also there have been more and more works recently on eye gestures, so that you have to perform particular gestures using either your eyes, so just moving your eyes quickly to the left, to the right to confirm a particular action, or more precisely to use your eye gaze, so you look at certain objects in a certain order to then issue a certain command. However, my work hasn't focused on this area, just to distinguish here. To make that clear, we really focused on the gaze-directed pointing and to kind of take benefit of the implicit gaze input rather than forcing the user to do some explicit eye gestures or something like that. So now I want to go into detail about some of our projects. I will start with gaze-supported navigation. So we have investigated different areas here. For example, how can users use their eye gaze to navigate, to steer in a virtual 3D scene? For example, also this is relevant, for example, for digital games, first-person shooters or something like that, where you want to move through a 3D scene. And also we have explored how you can use your eye gaze in combination with a mobile handheld, for example, a smartphone, to explore large data collections so that you could zoom in to a certain picture, that you can select a picture and so on. But now, on the next few slides, I will actually talk about our last project that we had done in this area, about more general gaze-supported pan and zoom, for which we have combined different modalities with eye gaze to perform pan and zoom operations. And first, I want to distinguish here, or kind of highlight the three different aspects you have to be aware when kind of designing for the pan and zoom, or when to distinguish also from other research in this area. And these are three conditions you have to be aware of. So one is the input conditions, of course. So does the user have to look continuously on at a certain region on the screen to perform a movement, for example, panning up or down? Or do I just start a movement, then it's moving, I can freely look around, so I'm not, this would address the double role of the eye gaze, so you can still freely look around, but you have to find a good way to stop the motion to prevent overshooting. On the other side, the speed can be constant, or you can gradually increase and decrease the speed using your eye gaze. And similarly for the direction, is it a fixed direction? For example, I look at a button, there a certain speed and direction is associated with this button, or can I gradually change the direction? Here just two examples for this. Here at the right from Adams and colleagues, they used kind of active regions, so you have to look at a certain region to perform a certain panning motion with a constant speed. And also down here, Hansen and colleagues used an approach where this panning speed would increase the further you look away from the center part, and also you could gradually adjust the direction. So if you look to the T up here, this would then move to the center. And here are, of course, a couple of risks for gaze-based steering. So there's a high risk for involuntarily issuing commands, because this approach, for example, was a gaze-only approach, so you had to twirl, then a certain action would be issued, and it was sometimes, it would raise involuntary movements. Also, the lost feeling of control. Often people run into overshooting problems using gaze for movement control, and it was described as overwhelming. And we wanted to address this with different combinations of eye gaze with different modalities, and for this we used a gaze-directed zoom, so you could simply zoom in towards what you're currently looking at and could adjust the speed and the input condition, whether it's discrete or continuous, using different modalities. And just picking one here, for example, the touch input was really nice for that. So you could have a large screen. So the idea was you can just step up in front of a large screen, you look at a target that interests you, and you can perform a very subtle and very low effort touch gesture, for example, moving your touch point up to zoom in or down to zoom out, and could also gradually adjust the speed. And here's an example for that. So the cursor is controlled using your eye gaze, which is up here. You look towards London, and there are very subtle, you barely notice that there are movements, and you can zoom in and out and explore, for example, Google Earth here. For panning, we also use a gradient-based, rate-based, and continuous approach. So what you are looking at would then move towards the center of the screen, and the speed would increase the further you look away, so that it becomes faster the further it is away, and then gradually gets slower towards the screen center. And it is a continuous input, so it would adjust all the time. However, it is not active all the time. So when you are not touching your smartphone, for example, to take the previous example, then gaze input is off, you can freely look around, and once you touch the smartphone, you indicate, okay, now I'm ready, I want to interact, and the panning would be active. So as a very rough conclusion, this approach, the gaze-directed panning, worked pretty well for slow panning motions. So if you're, for example, zoomed in towards London, you want to follow a certain street, for something like that, it worked pretty well. However, if you want to quickly go from, I don't know, Berlin to New York, and you are already kind of zoomed in, have to perform very fast panning motions, or want to perform fast panning motions, then it gets really overwhelming. So we wanted to address, or still have to address this or we have to keep that in mind for the design, of course, that for slow panning it is okay, but fast not so much. And the gaze-directed zoom was, all in all, assessed very positively. We have tried it out. I mean, I have demoed it at several conferences and usually got really, really good feedback. So that was assessed as very natural, and oh, I'm looking at that and zooming in there. And once you don't want to interact anymore, you just lift the finger from your touch pad or touch phone, and that's it. Also, we tried out different combinations of these aspects that I've mentioned earlier, and for example, also discrete input, so that you have to look at a certain area and so on. But the continuous rate-based and gradient-based combination was assessed as providing the highest feeling of control, and people really liked it, that they could still stop when they wanted to. They didn't feel so overwhelmed. And this is, of course, really important if you want to design something using your eye gaze. Also, kind of a work in progress, we have showed a demo at CAI this year in Paris using a combination of foot input devices with eye gaze, also for panning and zooming. And here the idea was actually to leave the hands free for additional input. For example, our scenario was that you have a geographic information system and want to annotate certain things on your map, and also, of course, don't want to, you want to continue drawing, and at the same time want to do some panning or zooming operations. So for this, we had kind of the setup with the Tobii TX300, which would then capture your eye gaze, and had these different input devices. So we had one directional foot pedals to just zoom in, and then another one to zoom out again, and also to, when the foot pedal would be activated, then also the panning would be active using your eye gaze. And then we had here, this one is a two-directional, actually a kind of a joystick kind of way, that you could also do fast panning motions just using your foot input. And then going forward and backward, you could adjust the zooming in and zooming out speed, and similarly with this two-directed foot pedal. So, potential benefits of this gaze-supported foot interaction is that, of course, we can address several of the challenges that I have mentioned. So we can compensate for unintentional activations because we have this explicit foot input, and the user can freely look around when taking the foot off the pedal. Also, it was described as having a high comfort because we can take advantage of very fast yet imprecise gaze input, and also, of course, we have this aspect of multimodality, so we still have the hands free, we can do other tasks. You can also imagine other application areas, for example, kind of 3D modeling, where you want to move around an object, but at the same time want to manipulate it, for example. So, as I have mentioned, this is still work in progress. We have gathered first user feedback. We also showed it to a couple, not only a couple, there were a lot of participants at CHI, which we asked, so actually experts in the HCI field, so that was really insightful, and are still working on more thorough evaluations, of course, really on the suitability and practicality in a real working environment. Would people really use it? How can they handle the primary and secondary input, and so on. So this was the navigation part, and now I also want to talk about the gaze-supported selection and positioning. So you can, again, imagine you're stepping in front of a display, want to select certain graphical objects, and maybe you want to reposition them, manipulate them. And for this, we particularly focused on a combination of eye gaze with ubiquitous smartphones, so that you can simply use touch input from your handheld. And we proposed the principle gaze suggest, so that we can really take advantage of very fast yet imprecise gaze input, and then have touch to confirm the intention of the user to select a target, for example, or to refine the rough input. And also, for example, to add additional actions, for example, manipulating, rotating an object. So first, we concentrated on gaze-supported selection, kind of only gaze-supported selection itself. And for this, we deliberately wanted to support not only selecting large targets and not only selecting targets that are maybe far apart, so that you can do kind of a snapping technique or something like that. Instead, we tried out very small targets also, small targets that are closely positioned, and even overlapping targets. And again, the scenario was that you have a smartphone in your hand and you want to interact with a distant display. And for that, we considered that you should be able to interact with your smartphone eyes-free, so that you wouldn't need to switch your visual attention from the distant display towards your smartphone all the time. Instead, that you can interact with your smartphone, not looking at it, and maybe just holding it in one hand, so that you only use your thumb to interact. Also, we wanted to address several challenges, of course. For example, how can we prevent involuntary actions that we can, of course, do similarly as before with the pan and zoom projects, by just touching the smartphone, indicating, okay, I'm ready, and lifting the finger if not. And also subtle gaze interaction, not to overwhelm the user. So how can we actually design a way to also not visually clutter the view too much to overwhelm the user? And how can we counteract imprecise gaze data? And there are several works on how to counteract imprecise gaze data. For example, zooming lenses, of course. It's not only in the eye tracking field, but also, of course, for touch input, where you can visually extend targets in motor space to more easily select a tiny target then. Okay. And there was actually another slide, I don't know where it went, about the magic technique, so that you could manually fine-tune your rough gaze-directed cursor position to then, also select small targets. You could use your mouse, for example, or in our case, we use a touchpad to then refine the position. But I will talk about that on the next slide. So again, here are the two main approaches to counteract counteract imprecise gaze data. The first one actually just is a very straightforward approach. You look at the target and you can confirm the selection. However, there are no compensations for imprecise gaze input. Or actually, I have to rephrase it. There are no compensations for offsets. So we did counteract jittery gaze movements using some filter techniques. Then the gaze-directed, now here's a slide about gaze and manual input, just to show you again. So this was the magic technique where you would use your rough and fast gaze input to indicate a rough area of interest. Then you move the mouse, your cursor would jump to the gaze location, and then you can refine the input using mouse input. And there have been other works, for example, kind of a sensitive mouse, which already detects when you're touching the mouse, similar to our approach where we touch our smartphone, to know, okay, now the user wants to interact, now the cursor would jump to the gaze location, and then it can be refined. Because here, in the first approach, there were some problems with overshooting, because you would look at a certain locations, and the movement of the mouse would initiate the repositioning of the cursor. So now to our techniques. The gaze-directed zoom lenses, we investigated different zoom lens behaviors. First, the zoom lens wouldn't be visible all the time to not distract the user too much. So once you touch your smartphone, the lens would appear. You can configure the zoom lens, for example, zooming in further or increasing the size of the zoom lens using simple sliding gestures up and down, or for the size to the left and right. And then we had these different behaviors. One is eye slaved, so that the lens would always follow the eye gaze around, so that essentially the gaze cursor is always at the center of the lens. This, of course, can be a bit overwhelming if you have a bit jittery movement, and although we filtered it out, you never really get rid totally of that. And on the other side, we had a semi-fixed zoom lens behavior, which would be stabilized or fixed to a certain location as long as you would look into that kind of proximity. And once you look outside, the lens would move around with your eye gaze. So just to show you an example, so you would activate the zoom lens, and you can then move the lens using your eye gaze. I mean, you cannot really see it. We use a very, very subtle cursor here to indicate your current gaze position, because usually it is advised to not show the gaze cursor at all, but actually I would always show the user at least a subtle feedback about the gaze location. So then we also had the magic techniques. One is a touch-enhanced gaze cursor, which takes benefit of fast yet imprecise gaze input, and you use the touch input to refine the cursor position. So one approach was that you have kind of this reference circle. So the circle indicates the rough area of your interest, visual interest, and then you can then you have a reference circle on your smartphone, and you can just tap quickly to then directly place the cursor accordingly, or you can do relative cursor movements as similar as on your laptop using your touchpad. And here's an example for that. So you touch, kind of a circle here appears, and you can quickly tap the cursor to the location you want to have it, or you use the relative positioning on your on your smartphone. Then we also had the magic tap technique. Again, we have this rough area of interest, and you can simply go through a list of target candidates, which are assembled based on which targets are in this or intersect with this circle. And then you can just go through this list by performing a simple horizontal sliding gesture, which turned out to be pretty useful for going through this list of discrete targets. And here's an example. So you perform a simple horizontal sliding gesture and can go through the list of targets. I mean, here the targets are pretty large. You wouldn't have needed it, but just so that you get the idea. So we evaluated these techniques with 24 participants, and also evaluated that for very different conditions. So we had large targets, we had them in the grid, we had overlapping targets with really, really, really small targets where it's difficult. So the task always was to select the yellow block here, and here you can hardly see it. So this was kind of the extreme. How can we still use gaze input to select something like that? And the third task scenario was kind of a desktop mock-up. And in our evaluation, we also assessed task completion time and error rates, but really wanted to find out what works well for users. So where do they see shortcomings, and what about the general usability? How do they assess that? And of course, you can find the details in our paper from Kai 2012. But just to give you a very, very rough summary of our conclusion here. So although the gaze-directed cursor, as I have mentioned earlier, didn't have any compensations for offsets, and so where it was pretty much impractical for selecting small targets, it was still assessed very easy and effortless for large targets. And a lot of times users tried to just look at a target and confirm the selection a couple of times instead of using maybe a zoom lens or to perform some manual fine positioning. On the other hand, the gaze-directed zoom lenses were also, or both manual fine positioning and gaze-directed zoom lenses were found flexible, simple, and fast, so people could cope with them. However, the gaze-directed zoom lenses, once you zoomed in very much for very tiny targets, it showed to be only useful kind of in a limited way, because people would kind of get lost, they didn't really know where they were, and it was partly distracting due to the visual clutter. Whereas the manual fine positioning was in general assessed very positively. We had kind of a problem with the implementation. There was kind of an overshooting of the touch input, but this was simply due to a lag in the communication between the smartphone and the computer. The interesting part here is actually that the Magic Touch was practical even for very tiny targets, and so if you only have the task of selecting something, kind of such a simple way to go through the targets seemed very useful. However, we also thought about, well, usually you do not just select targets, right? I mean, you would select, and what then? Usually you would go on, maybe reposition a target, maybe also manipulate it, resize, rotate the target. So how do the techniques apply to that? How can we use, for example, Magic Tab in such a way? And here it is actually not so practical, because it is very difficult to fine position a target on a white canvas using kind of such a technique then. So we investigated this further, elaborated a set of very simple touch input, again, where you don't need to actually look at the smartphone to interact with the distant display. And for this, we deliberately, again, wanted to support not only selecting large targets and not only position them roughly, but also what about small targets and fine positioning them, a very deliberate outlining, layouting, for example, of targets. And also what about different transitions? So on the one hand, I could distinctly select the target, maybe resize it, and later on reposition the targets. Or what about kind of a drag and drop? How can I support this using gaze input? And for this, we considered kind of a drag and drop approach, where we have defined kind of this proximity around a target. So while you look within this proximity, that target would not be repositioned, just be selected, so that you can address imprecise kind of jittery gaze movements, and that the target wouldn't immediately jitter around with your eye gaze, and only when you kind of leave this proximity, you would start this drag and drop process. Also, for the zooming lens, we noticed that only using your gaze to then reposition something using a zooming lens is we run into problems there because of the double role of our eye gaze. Users wanted to observe whether an object would already be correctly aligned and then accidentally reposition the target. And so to address this double role of the eye gaze, we used actually a head-directed zoom lens. So we could still kind of take benefit of the rough visual field of the user, but lift the problem with a double role. But on the other hand, as a shortcoming, it is more explicit and was sometimes even described as a bit straining from the users. So, and here's just an overview of the different interaction set that we have developed, where you can see, take this one, the distinct. So you can just, first you can adjust the zoom lens, the head-directed zoom lens, using up and down and left and right touch gestures to increase the size of the zoom lens, to zoom in further. And then you can just look at a target, double tap, then you have selected the target, and look somewhere else and reposition the target by double tapping at the destination again. Whereas you can also just look at a target, touch your phone, look somewhere else, initiate this drag and drop procedure, and then just release the target at your desired destination. So here, to support the precise selection and positioning, you would have to zoom in at the beginning, whereas with a touch enhanced gaze pointer, you can, of course, still refine using the cursor using your touch input. So here's an example from our setup where the user actually had a head-mounted eye tracker and had to interact with the distant display. For that, we used the Arrington Research point view eye tracker. We also had to track, of course, the head. So we used an OptiTrack system for that and used a Samsung Galaxy to then, as a smartphone. So here's an example for that. Here's a head-directed zoom lens, which you can see up here. It's a bit difficult to see, but you can just look around and initiate different rotations and translations then using your smartphone by putting it to the side and then resizing it, for example. So with this, we could support, with the multimodal gaze supported combination, we could support different input conditions, fine and coarse, selection and positioning, and also different transitions between distinct and seamless selection and positioning. The combination of gaze and touch for these tasks were assessed as practical, effortless, and fluent. Some kind of conclusions we had for the touch-enhanced gaze pointer was that it is very fast, but it took users time to get used to because we had, of course, a couple of participants who haven't used eye tracking before for interaction, and so it was kind of overwhelming for them at first. For the head-directed zoom lens, this was less overwhelming, or at least users described it as less overwhelming, but also was described as a bit more unnatural for precise positioning using this lens. I would have preferred to do some manual repositioning. So, summary and outlook. So, in my work, I developed and investigated, of course, novel gaze-based interaction techniques, and we have carefully designed new ways for convenient gaze interaction. So there has been lots and lots of work on using gaze for interaction, but not so much for convenient use, rather to allow people with disabilities, for example, to actually interact with human computers, for human-computer interaction, sorry. Then gaze-supported interaction. We really stressed this term, gaze-supported, because we really think there's a high potential for using gaze as a supporting input modality, and that's why I put a particular emphasis on this, to use it in a more subtle way, and also to take advantage of fast, implicit, yet imprecise gaze input. Finally, also the multimodal aspect. So we thoroughly examined several different combinations. Not all, I couldn't discuss all now, but if you have any questions later, you can ask. And for us, however, a very, very interesting combination was the combination with gaze input and ubiquitous smartphones, especially kind of having this scenario in mind. You're just stepping up in front of a large display, public display, for example, and can start interacting with that. And also the proposed principle of gaze suggests and touch confirms, whereby the additional modality, in this case touch, not only confirms but also, of course, refines rough input and also allows for additional controls such as rotating a target or resizing it. So my work was limited in the way that there are, of course, a lot of different additional investigations that you can pursue for multimodal gaze-supported interaction. So we have focused mainly on basic interaction tasks, navigation and selection and positioning. But there are a lot of interesting additional research questions. For example, what about the practicality of gaze interaction in everyday contexts, also in an office scenario, but kind of for prolonged use, Also, what about gaze-based interaction for multiple users, or for example, for collaboration scenarios, and as a more passive means of interaction, so for attentive user interfaces that, as I've mentioned earlier, that devices are actually aware that you're looking at them. For example, this is pretty interesting also for human-robot interaction. Then context-sensitive information adaptations. This is interesting for multiple display setups, or also for very large screens where you may have a different distance to the screen and certain details may be only revealed to you once you get closer, and kind of the fine details. And finally, also always a very interesting area are novel gaze-based game mechanics, because you can play around with a lot of very creative and new ideas. And here just a few more examples that, of course, you can also consider further or additional multimodal combinations, so that it was also kind of a limitation of my work, couldn't look at all of them. So a very interesting combination would be, of course, to combine it with brain user interfaces, also with hand gestures in front of a display, or kind of proxemics, location, and this orientation of a user towards the display, and speech input. And also, there are various application domains that could benefit from subtle and seamless gaze-supported input. One is, of course, are scenarios where the user's hands are already busy, so they have to find other ways to interact with the system. Also for kind of these very multi-display setups where you may want to attract the attention of the user, want to lead kind of subtle gaze aids that you lead the user to a certain information. And an area which I also find very interesting are, of course, augmented reality setups and how to interact with them using, for example, your eye gaze. So, thank you for your attention. Yes.
Very good, thank you. So, a little bit of time for some questions. Yeah.
You mentioned public displays. In all the studies you did you always assume that you take the user and you calibrate the eye tracking for them beforehand? Or are you able to avoid the whole calibration annoyance by using an additional device for confirmation, refinement, etc.? Because I've found most eye tracking that I've participated in, it's the constant calibration every time you sit down, a new user, or just walk in, you sit down in the chair, you move the chair, okay, you recalibrate to get anything. Can we just get rid of that calibration?
I'm not sure if we can totally get rid of the calibration. For our scenarios, we just assumed that the calibrations would improve, and that for some setups, you may not require totally precise eye tracking. So there have been studies where you just use the very rough gaze estimation, and this would be sufficient for interaction. And also, actually, an idea that we had was, of course, you have kind of these intrapersonal characteristics of your eye gaze. So you could actually, with your iPhone or your smartphone, could authenticate yourself walking up in front of the display, and then it just grabs this information so that you can interact more conveniently with it. If you don't want to share your information, then it's more roughly or something like that. So there are kind of ideas to address this, but it wasn't the focus of the work. Yeah.
Thank you. Very interesting. I guess most of your work is related to large displays rather than just conventional workstations.
Yeah.
Conventional workstations, frankly, touch input is probably going to work best. So I was wondering what you were using as the control case that you were making the comparisons against. So when you tested gaze input, what was the control system? Do you have a view as to what the standard method is for interacting with large displays against which you were comparing your techniques?
We didn't compare it to techniques for large displays, because the eye trackers, so that was kind of the main scenario we had in mind, that at some point we could interact with large displays, but the eye trackers that we mainly used were in combination with some desktop screens. So what we there used was simply mouse input. But what we were actually more interested in was not so much the performance in terms of speed or something like that, but rather how do people like it? Where can we improve the techniques? Because we are not at a point where they are already totally optimized, and there are, of course, certain issues even with these works where we see improvement, or where we see things that could be further improved. And once we get to that point, I would compare it to a strong baseline or something like that. But until then, it was rather really finding out, okay, what do we have to consider for the design of such techniques? Yeah.
So, for example, what immediately came to my mind, I'm afraid, and perhaps what you would describe as prejudice, but that's, I have to say, it's on the basis of experience. Like, I've tried to do this and failed a number of times, so I'm always impressed. But I wondered if you just tried taking the touch input on the smartphone without the eye gaze and use that as a comparison.
But how do you, so no pointing at all, or what do you mean?
Or something on the smartphone. If the person is holding a smartphone, I just have a sneaking suspicion that the eye gaze, in addition to the smartphone, is probably slower than just some cunningly devised interface on the smartphone alone.
Showing the same image that's on the large display.
Not necessarily, no, just using it as a touch tablet of some sort.
I see.
We actually tried that for the head-directed, for the last project that I have described. So you could actually don't use your gaze pointing at all and immediately start just using touch input if you don't want it to use your eye gaze. But the thing was that if you have a large display, I mean, you could do some kind of speeding up, so that you need some clutching, and sometimes people rather like to look at it and do a small movement on the touch tablet instead of clutching the cursor until it's at the right position. So that was the difference, and actually it worked pretty well, so that wasn't so much an issue.
I suppose there's also the tilting of the phone, and using the accelerometers is another possible.
Yeah, we tried that, but unfortunately this wasn't assessed so well, because there were a lot of Midas touch with the smartphone actually, so that people would, I mean, they already tilt their phone, and then unintendedly they would they move something, because we used that for the panning, and then people say, oh, but I didn't want to pan, and something like that. So it's a bit tricky.
Yeah, just one of your slides indicated something that I think we found a little bit in some work we've done this, is that the Magic Tab system, which is one of the things you got, that was quite popular with your users, was it?
It was comparable, like the user assessment was comparable to the Magic Touch, but the performance was much better with the Magic Tab.
Yeah. I was wondering too, when you did it, as soon as you started tabbing, was the gaze still used? Like, did you sort of fix the gaze point and then tab there, or was it a sort of continual updating of the tab region as you moved your eyes?
It was fixed. Once you touch the phone, your gaze input is off, and you can just concentrate.
Tab around on the things that you had looked at.
Yeah, exactly. The moment you touched, this gaze position would be used, and then yeah.
And also, it seems to me that another application is sort of choosing a sort of hyperlink on a sort of web page.
Okay.
That the Magic Tab would be particularly good for that. Did you look at that application?
Say again?
Did you look at that application?
We didn't look at that application, but it is a good scenario where I would see definitely, yeah, that it would be useful. Yeah, but we didn't try it out.
Our eyes already have a magic zoom in them, right? There's a foveated sensor region, so if I look at the word V in Field and Dank, I really can't read the U. I might think I can, but I can't. If you had perfect gaze tracking, and people in the 70s used to implement this by gluing a needle to the eye and then putting a picture on the end of the needle, you should not notice the magic zoom at all. Right? You should be able to just enhance foveation, I think.
But there are certain limitations to that. I mean, if you have a really tiny target, let's say, I don't know, the eye of the picture here, like that, then it's difficult. I mean, what do you precisely want to select? So it's similar to the touch input. I mean, it is rather rough.
But is it rough because, I guess what I'm getting at, is it rough because our technology is bad? I mean, I feel looking at the dot at the eye of auto, I really feel like I'm focused on that eye. I don't think I'm jittering. Am I really jittering?
You are jittering, first. So there are microsaccades. But for some diseases, you actually can notice the jitter more. But usually, like in a normal, healthy human being, you don't see that. And actually, the foveal vision is still imprecise. So if I'm stretching out my arm, the focused area is actually the size of my thumbnail. So now imagine you're sitting there and there's a display. It is kind of a cone thing, not as much. There is a certain distance, so you cannot see something totally precise at a very large distance. So there are certain aspects you have to consider for that. And it's actually similar to kind of hand-based pointing or something like that. There's also kind of a jitter. Small movements at a distance make a big influence, of course, and it's similar with the eyes. So there are kind of two aspects to that. One is the physiological aspects of your eyes, and another one is really the tracking itself.
How big is the microsaccade in pixels on this screen?
Say again?
How big is the microsaccade?
I don't have numbers for that. I don't know.
One last question, anybody?
I was just wondering, if you were to combine the gaze with the touch like this, is there still a place for gaze-only control mechanisms? So, you know, to do eye-only activations. So, for instance, sliding a point along a slider to activate it or something like that. I'm just wondering if you see where we're going as the mixture of gaze and touch, but will there still be some like buttons that you press with your eyes or that you activate?
We didn't use it, and I mean, you could imagine some combinations. For example, if you look at certain information and maybe there's some additional information then kind of shown when you look for a prolonged time at it. But we didn't really use kind of this combination of gaze only and multimodal. If that was your...
I was just wondering if there were alternatives for the hover interaction, but that's 4 different papers. So.
Hover interaction, yeah, no, we didn't. I mean, we did it in a way that when you were looking around, like in the selection scenario, things would highlight if you look over them, but that was kind of it. We really wanted to leave it at a subtle interaction.
And that is modeling gaze as a point rather than as a cone that can change at radius. I'm wondering if you use the radius in any of the interactions.
Actually, we didn't. I was thinking about it, also kind of the distance to the screen and so on, but actually we didn't use that. But it would be interesting maybe to look into that further.
Well, thank you very much for a great talk.
Thank you.